As we look at particulate diagrams, there's lots of right ways to show different reactions. So as we come to look up at any or all of these, there's too many to choose from, so I didn't try to do all of them. One thing we would want to do is be very careful whether we're showing things bonded or separate and how they are different. If we chose this example right here, we might want to show H, Cl, Na, C, and O as maybe spheres or circles of different colors, and then how they're bonded together at different times, accounting for even the states of matter. Anything with a net or a complete ionic showing separate versus together is a great way of representing it as an ionic equation. The potassium, the sulfur, the lead, and the acetate were all separate at the beginning. The potassium and the acetate were still separate at the end, but the lead was together. And showing that 2-to-1 ratio of ions to product is a great thing. We could show just the net change in any of these as well. But really, if we're looking at an aqueous solution, most of the time we would focus on our complete ionic. We would show all of the ions as separate and then how they look when they're together. Remembering polyatomic ions like OH could be represented as a single particle. They could be shown as an O with an H. A nitrate could be an N with 3 O's, or it'd be totally great just to have a large circle marked or shown as a nitrate. As we come down here, we would have the same idea, probably focusing on the ionic equation, really paying attention to our ratios and what starts separate and together. With hydrofluoric acid, it would be a little bit different because we would want to show that all or most of our HF is still bonded, but then it changes and F- is by itself. The sodium, however, is all by itself the whole time. So this would be a good one that could show a lot about the acid strength as well as the reaction that it's occurring, even though everything's in a 1-to-1 ratio. We don't too often do them for reactions like in number 1, in number 3, or in number 4, except to make sure that we're showing our ratio. And as we'll see coming up, thinking about our stoichiometric or our stoichiometry ratio, our 2-to-1 making 2, our 1-to-3 making 2 and 3. So making sure that we've got those right ratios. And if I had too much oxygen or too much ethanol in there, that some of that is left over on the other side, just like in the examples we looked at. So all of those are great, but we're paying attention to charge, what particles we're showing. And really, initially, we're going to do a lot more where we're looking at diagrams, and then we get into the practice of drawing them. So as we look at this, it asks about a hydrogen and a bromine reaction, writing the molecular equation for that particulate diagram and everything else that we can know. So first of all, it's very simple. We've got H2 and Br2. That reminds us that they're diatomic. It makes HBr. It shows kind of that it's a multi-picture process, meaning that it doesn't all instantly click and happen at once. But we do see 2 product molecules for each molecule of hydrogen or bromine that is consumed. And then as we get here to the end, we would notice, well, there's still some hydrogen. Yep, there's still some bromine. So we can still continue the reaction. The reaction's either not done or there's something else we need to know about that reaction. So we've got a picture over time. We're counting, we're paying attention, and we're looking at what we're starting with and ending. And as we get into more complex types of reactions, oxidation reduction, acid base, we'll see these even more and more.